Okay. Moving on to chapter 9. I updated all the grades for the tests. So all the updated grades are in Hawks. I'll put the new grades in Blackboard probably this week sometime. I might get it to this afternoon. I'm not sure yet. And I'll update the homework grade based on where you are on the homework in Hawks at that point. So, all right. So we're going to move into chapter 9. So chapter 9 actually really expands on the stuff that we were looking in chapter 8 and whatnot. So it's not going to be very much different. We're just going to look at a different way of looking at sampling. So the first thing we need to understand is what is a sample and how do we work with it? When you get up in the morning and hop in the shower, do you literally turn on the water and hop right in the shower? Like immediately and not even check and see if it's like not freezing? Normally you put your hand in, right, and make sure it's not freezing. So you're like, because you don't want to get in really cold water. Do you test every single droplet of water? No. Put your hand in. You're testing basically a sample of that water. All right. So you don't know if the next water droplet that's going to come out is going to be hot or cold, but you're testing a sample. So when we're looking at doing large-scale statistics, we're never going to be able to test everything. But we can test samples. And if we test a bunch of samples, we get a really good idea of what's going on across the entire country or state or whatever we're looking at. So you see this a lot of times in polling where you see a poll of polls. So every poll does their own questioning and whatnot. And then there's people that'll take all those polls and put them all together. That's looking at the sampling of them. They're taking every one of those as an individual sample, and then they're putting them all together to say, okay, what is it going to look like in general? And that's what we're going to look at this week. All right, so here's a picture of a plane that came back and landed safely from World War II. All the red dots are bullet holes. Okay? If we're going to make the plane safer and we want to add armor plating, okay, to make sure the plane doesn't crash or get shot down, where should we put the armor plating? So like here, 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 and here? Everybody agree? Okay. You didn't save anybody. Listen back to what I said. So this is a plane that came back and landed. Why? Right, because the planes that didn't come back probably were shot there. Okay, so if you think about it, these are the spots that weren't hit. This plane came back and landed. This survived. The ones that never came back, we don't have any data on them. All right, so like, okay, well, then my guess would be they were probably shot in like these parts here. That was the more important pieces and hit something. Let's put the armor there. Okay. This is known as bias. When you're looking at, this is specifically known as survivor's bias, actually. When you're looking at why something survived, you think, well, I did this, this, and this good. And sometimes it's not because of what you did good, it's because of what didn't happen to you originally. Okay. In this respect, the pilot might think, oh, it was amazing, I did great. They just didn't get that one lucky shot where that was going to cause damage. So when you're looking at data, we need to look at those type of situations to eliminate that bias. So, and a lot of times we look at that. Like that's the type of, when we get that information back, Like, this is the information we have. How do we use that information? So bias samples are ones that overrepresent or underrepresent some segment of the population. So in that respect, the bias was we only saw the ones that survived. We didn't see any of the ones that didn't survive. Okay. Which means we don't have data on that side. And it might have been that those spots didn't mean anything, but we don't know that. So we can only go based on what we have in that respect. So when we're looking at sampling, we want to make sure that it has a good cross section of the population. And that's very important when we're doing any of our studies. What's tomorrow?
Election day.
Election day. And so this is where statistics becomes reality. Up until tomorrow, we have statistics. We have polls, we have data, we have samples, we have all this stuff. Tomorrow, on election day, when the polls close, we have reality. That's actual information. It doesn't actually become real until they count all the votes and actually put it in. They will call states before that point, before all the votes are cast. You'll see them call states and there's no votes like counted. Like, I guarantee Connecticut tomorrow at 8 o'clock will be called. Okay, with no votes counted at all, they're going to tell you Harris won the state of Connecticut. That's because of past data and everything else that they have there. However, when they count all the votes afterwards, that can change. And we saw that in 2000, probably before most of you even, like, some of you were alive and most of you actually were paying attention. In 2000, they called Florida. And then they changed who they called Florida from. And then they changed who they called Florida for. Florida went back and forth like 3 or 4 times because they had data that came in, and then the data that actually came in afterwards contradicted what they thought was going to happen. So that's where that statistics plays a role. Once everything's counted, we no longer have to go on statistics. We have the actual hard numbers, the actual basically census data of it. We have the actual full information. So depending on how they do that sampling and that statistics and stuff beforehand, they can have that bias built into it. And unfortunately, sometimes we don't know that. We don't know that until afterwards. All right, so apparently I put that there twice, which isn't good. The first thing we're going to look at when we're looking at two slides. Where is? Oh. All right, so the sampling frame, before we start actually picking information and coming up with how we want to actually do our study, we need to identify all members of the population. And depending on what kind of study we're doing, depends on what demographic information we need to look at. Right? So if we're looking at the types of ice cream people might want to buy, economic data might be important. Okay, so if you go to the ice cream aisle, the basic flavors, sometimes you can get chocolate and vanilla and stuff pretty cheap in the generic brands, but you're probably not going to be able to get Rocky Road a little cheaper, or Moose Tracks, or cookies and cream, things like that. So if we're looking at favorite ice cream, economic data might be important, because if you're on a poor, you might only eat the basic flavors. Or if you have a lot of money, you're going to eat more exotic flavors, and those might be your favorite ice creams as compared. So that might be something to look at. I can start to see how other types of data can influence our decision making. So when we're looking at creating that framework, we want to decide that aspect of it. So how do you pick your people? One way is just a simple random sample. Keyword being random. Okay. Random is the most important piece here. No matter what we do, it has to be random. Right? There's lots of ways we can do random samples. The easiest way to do is turn everything into a number, and then just have computer randomly select numbers. All right, that's the easiest way to do it. Most computers can actually do random number generators and actually select them pretty quickly. If you have names and stuff like that, sometimes random samples or computers can also do the random samples of that. That's easy enough to do. If you put all the people's names in a list, say I'm taking the fifth name, every fifth name, that's random. Okay? As long as you don't put all the names in order. Once you put them in order, it's no longer random. But if you just have a mixed up list of names and you pick every fifth one, that would be random. All right? It's like having a shuffled deck of cards and picking every fifth card. It's a random sample. Does that make sense? Yes? All right. All right, read this problem. All right, so you are all college students. If you got mailed a questionnaire regarding insurance programs from the school, what would you do with it? Why?
I don't know. I feel like when I get an email, I just think it's fake.
Okay,
So
that's fine.
maybe if it was my email, I would answer it.
More likely to answer it in your email. That's interesting.
Yeah.
All right, what about you?
Their parents' insurance until they're like 25. So you have your own PIN. So like that was instantaneous to get on the school insurance. That would also question like credibility.
Okay. That's changed drastically, by the way. It used to be like when you got 18, you were off your parents' insurance.
Yeah.
Now it's changed to 26. All right. What about the rest of you?
Personally, really bad with surveys. Like I'll open it and have every intention of doing it, and then it sits on my counter, and the time's out before.
All right. What if this survey had a $5 bill in it?
I would do it. And I
Would you keep the bill and send it in, or would you just keep the bill? You would still forget. You would do it though? Okay.
Because I feel guilty.
Okay.
I feel like a survey should definitely be done on like if it was just mail, if it was information, then mail, but like surveys are like they're just more convenient electronic.
Okay. So if it was electronic, if this was emailed to you, you'd be more likely to do it or less likely to do it?
More likely.
Okay. Why would you be more likely to do it? Just because it's convenient?
Yeah.
Okay. Yeah.
I would trust it more. Because the thing is that I would question whether, if it was mailed to me, I'd question whether it actually came from the school or not. If it was coming through my school email and I saw that it was from the school, I would know, and I'd be like, okay, fair.
Okay.
I'll do it. Yeah.
This is a generational change. And this book, I don't remember when this book was written, but that's a generational change. And I think it's interesting that you would trust the email more. I think our IT department would not be happy with that. Because that means you've clicked on a link that you might not have known what the link was going to, and then given it information. So I'm going to go with the IT department would not be happy about that information. But it totally makes sense. Yeah.
It's like a banner across.
Well, it depends on, like, yes, it should say something about it's from the school, but it depends on, it might not be necessarily from the school either. Like, it's saying, this is students in the marketing class that were doing it. So it might not have necessarily come from a official school email. It was like, it might have come from a group of students in that class. They were doing a study to figure this out. So that piece might not have been there. So, all right. So I guess the question is would this be a good random sample? Yeah.
I'd say so, because I mean, generally, well, yeah, no, I'd say so, because all students would be equally likely and unlikely to do it.
Okay, so we'll go with the randomness. We'll assume that we'll claim that it's random. So they sent it out, they got 50 back. Is there any biases in the responses? Okay, so all right, not quite the bias we're looking at. And that's actually really important. Hold on one second. Let me explain this piece because that's actually the response I was looking for. But it's actually very important because we're not looking at biases and what type of responses we're getting. We're looking at biases in terms of how they would have chosen to do it. So like when you said, okay, I'm just very forgetful. It's like, I have every intention of doing it. I'm just not going to do it. So like, we're going to lose out on that group of that possible population. Most of you in here said, if you're mailing it to me, I'm not going to trust it. Like if it was in my email, it'd be different. So we possibly could be losing out on the younger generation in this respect. The people who are going to submit this back are older generation. Or where you were saying, I don't really give a crap about insurance because I'm not 25 or 26 yet. And I didn't install my parents. So why would I care? So again, so that's the bias we're looking at. Remember that the bias is what are we looking at the entire population of students? And if we're underrepresenting groups, then that's the bias we're looking at. Okay. So, okay. Now,
I was gonna, to me, I don't know if that's what you're asking for, like bias and statistics, how it affects the data.
right.
Like, what I said, like, people who might really need insurance would be more interested in taking a survey. versus
Right.
people economically, like people who don't have access to insurance or don't have access to parents that have good insurance,
Yeah.
that would be my guess.
Yes. That would be an internal bias in the way that this is done. Yeah. Okay. Yeah. And that's the thing. It's like, when we're looking at bias, like we have an internal representation of biases. Like, it's like we're against these people are against somebody and things like that. Like racism a lot of times was related in biases and those type of things. But when we're looking at statistics, it's not that type of bias because, in all honesty, we kind of want to see those things. We're looking at a bias. Are we underrepresenting people? Are we overrepresenting people? Are we overrepresenting a specific type of group? And that's where those demographic shifts and stuff like that we want to look at comes in. In this respect, we're going to get that. The people who really need it are going to be the ones that are most likely to send it back because they're more interested in it, right? It's like, Les, give me more information about this. And if we look at the results here, we had 50% of the respondents were very interested, 15% somewhat, 10% interested, 5% not very interested at all, and 20% not at all interested. All right. So do we see the bias show up in those results? Yeah, because you were saying the ones who are most likely to respond are the ones who are probably interested in insurance and needing that, right? So they're going to be very interested in this type of information. The ones who are forgetful and everything else would fall in that middle group. It's like, all right, I really don't care enough. It's like, it's not like at the top of my mind. So it's like, you're going to have those people that are going to fall into this group down in here. And then the ones who truly don't care, like, I don't want it. As crazy as it sounds, those are also overrepresented a lot of times. The two extremes are where the biases typically show up the most. All right. So that's where you're going to see the ones who really want it or really care, or the ones who don't care at all and want to tell you they don't care. Okay. They're going to be the two extremes in your biases. Yes.
Would it be true to say that this also goes for politics?
Oh, yeah. Yep. And that's why when we're looking at polling data and everything else, you have to be very careful in how you ask your questions. And you have to ask your questions in multiple different ways to determine if they're really giving you valid information. The other thing you'll see a lot of times when you're asking questions is the people will choose the first answer you would say or the last answer you say, especially if you're verbally asking questions, because they'll stop listening after the first thing. And then they might catch the last thing you say before you actually ask them their opinion. So the first and the last ones tend to be overrepresented in terms of their answers, which normally, if you're asking a list, is in extremes. Yeah.
If I look at the number of surveys that are, well, in this circumstance, that are distributed, because, like, I mean, when you said the politics thing, is the fact that, like, I can go down the street and there's like loads of Trump signs on each
Yeah.
house. But then if I go to every other house, there's no signs whatsoever for anyone.
Right.
So that would, at first I would think, everyone's supporting Trump, but the reality is that most people don't care. It's just
Correct.
on the street that way they care.
Right. And that's actually one of those things that you'll see. And like, that's actually a really great example that you can visualize right now. Like, you'll see the people on the extremes will have the signs one way or the other. The ones in the middle that they might care, they might not, but it's not like the most important thing in their mind. They're not putting up a sign. So that's that middle group. That's a lot underrepresented. So like when you drive through a town, you might see a bunch of Trump signs or a bunch of Harris signs, depending on what it is, but it's not going to be at every house. So you might get an impression of what that area is based on the few signs that you see, where you might not be seeing what everybody else that's not saying anything is. And depending on which direction the town is going, you might have people who don't want to put up signs because they fear retribution from the other direction. So you have that aspect of it too, especially in politics. So in this case, they sent out 150 surveys, they only got back 50. And of those, 50% said they were very interested. So how many actually were very interested in the actual 25? So only 25 people out of the 150 were actually really very interested in it. So the question is, you've got your data back. Is 50% a reasonable estimate of the proportion of students who would be interested in the entire college? No. All right. It probably is closer to, let's see, 25 out of 150. So we're like at, yeah, 15, 16%. All right. What strategies could they have done to better made their survey or gotten a better response? I think we said one, email instead of mail. That would have been one. Yeah.
Just handing it out in class and just don't write your name on it. You just like how we used to do our surveys like for our classes.
Yep.
We used to just like fill it out at the end of the semester and then turn it in.
Okay. So here's the question. Remember, that would eliminate some bias, but would it be random? If I asked everybody in this class, would that be a random sample of the college? Yeah. That's the key. Yeah.
Classroom and then only chose like literally like random ones out of the class and then combined all of them.
If they did it in all the classes, like, so that's the thing. It's like, depending on how you're going to pick your random samples, you can do different ways to do it. And we're going to talk about a little bit more of these on Wednesday. But like, you don't necessarily have to ask every class, but you could ask a random sampling of the classes. So like, I can go down the hallway and I'm going to pick 2 classrooms out of every hallway. and ask those questions. Like that's actually what's known as cluster sampling. We're going to ask everybody in that classroom, but the classes are chosen at random. That's where we can get the randomization in there. So there might be some other ways to doing it in person, doing it through email and those type of things like that. That would help eliminate some of the bias, but even that wouldn't eliminate all the bias. So yeah, we definitely need to think about other ways to be able to do it, but we can't eliminate the random aspect. Because if we just ask everybody, we could literally send out and ask every single person in the college what it is and require a response, and we get that's basically what your voting is. Then we'd get a true representation of it because we'd have all the responses. I will say, you guys say, oh, email's great. The amount of responses from when we used to do the surveys in the classroom at the end of the semester to now having it digitally and everything else online is tremendously worse. Like the actual in-person surveys, when you guys would fill them out and turn them in, were so much better in terms of data and actually response rate than the online ones. Yeah.
That's because you had to do them while you were sitting here.
You did.
Online, it's just oh, get that done at the end, for the end of the week.
Right. And a lot of people forget. And again, it's that bias. The people who are going to fill it in are on two extremes. The ones who really like that teacher and wanted to fill it in to give them the response, or the ones who really hated that teacher and again wanted to get the things in so they heard about it. That's what you get. You don't get a lot of the in-between stuff. So it's important. Trust, I'm telling you, it's important. Fill those things out. We actually look at those. Yes.
Say, couldn't they just do the survey or with a larger sample? Wouldn't that eliminate some of the prejudice? So a lot more in the middle ground to be represented, or
You would get more of the middle ground, but you'd also get more of the extremes. Yeah. So doing more doesn't necessarily solve that problem. It's still, the balance still ends up being the same. It's we got to do something else to engage the middle. And that's why some of the surveys literally do pay you. They'll give you a $5 bill or a $1 bill or something in the envelope that'll say, here, or a gift card. You enter, a lot of times they'll put it as fill the survey out and you're entered for a gift card. Just those little things, will get more people to fill it out. Because it's oh, I might get something. Yeah. And I'll come back to you.
Oh, I think I was just gonna say that also part of it is the online, your name's not connected to it, so there's no penalty for not doing it.
Right.
But in class, just accordingly.
Yeah. That's true.
Also, something you said at the online is the fact that everyone that I know, almost every guy that I know that goes here doesn't check their email. Almost everyone that I know checks their email religiously here. And it does create something of a bias there.
y'all need to set this up.
I know. No, I need to check my email more, but the point is, there's a bias there.
That is possible too. I don't know. I'm one of those ones. I have my email literally on my screen at all times. So I'm always on my email. I think that's a generational thing. I wonder if you got instead of email, if it was through a messenger thing on your phone or whatever else, you'd be more likely to respond to it. It's one of those things. That's the generational change. Is how does the generations communicate? So we made a major shift from landlines and home phones to cell phones. Most people don't even have a landline anymore. Very few people have landlines, and they're normally older. And then, so now we went to cell phones, and there was rules in place that they couldn't just randomly call your cell phone. That has now changed. But it was the cell phones were kind of off limits because, and at the beginning, you paid for all your minutes. If they called your phone, you were paying for that phone call. So you couldn't call. Now that it's all unlimited and stuff like that, that has changed. But so now it's I don't know a lot of the younger generation that actually would answer the phone for anything. Don't call me, text me. I am not going to respond to your phone call. Just text me. And if you call me, I'm probably going to text you back. So it's that is as a change. And now it's it's even moved past text messages. It's okay, now it's a WhatsApp or an Instagram or a Facebook message, or it's a Snapchat, things like that. It's other messaging systems on how you're going to use it, not necessarily the SMS text message that's built into your phone.
That's just so oversimplified. Probably what should be in my email, maybe like a social media setting. It's like,
Yes, and it's that number thing. It's like I see the little numbers on my screen. And it's like, oh, I got to clear that number off. And if you have too many of them, it's like, yeah.
Personally, I don't want those fixed. You know, like when I want to know something about school, I want to be able to just go directly where I can see something. about
Yeah.
it, but you fix it, so like, it's everything that is like my personal life and school, and I'm dating people, so it's like.
Again, it's just a matter of like, so that's the question. Even if you forget about school, like in general, it's like, where would be the best way for these people to get the data so that they don't underrepresent an entire generation? Remember back what I said at the beginning, at the very beginning of class, it says, who answers the phone calls for the pollsters? The old white lady sitting at home. Okay, that's the generation that does that. Yes.
There's some, I mean, going back to the politics of it, the fact that like, there is also I mean, this was even the same back in the day. This is nothing new.
Oh, no, it's not.
Younger people have less of an interest in taking surveys and answering these questions. I bet. Because
Oh, absolutely.
generally have more nihilistic approach to politics.
Yeah, and it's always been that way for anything. It's like, so, but that's actually, but that has a major impact on the data you collect. Like, how do you collect that data well to be able to represent those groups, because they actually mean something in terms of the outcomes? Like, not even just with politics, it could be with the type of car they're going to be going out to buy, or what's the new favorite toy that's coming out. Like, those type of things all matter to a business's bottom line. So we've got a lot of push now for like electric cars and stuff like that, but is that what the people who are buying cars actually want? Or is that the push? So it's like, it's a matter of, we need to talk to all the different generations. Like, yes, the younger generations want more economical, more things like those type of things, but are they the ones that are going out and buying a $70,000 car? No. Yes.
But what if in circumstances like with cars where, and this happens a lot in business, but people really don't know what they want. I mean, I think when you say cars specifically, I think like a Homer car from The Simpsons, where Homer is like trying to like, where they ask Homer to, you know, make the car of his dreams, like what the car he wants to make, and he makes the worst car in the world.
Yeah.
And, yeah.
Yeah, like the Cybertruck.
Exactly. And no one buys it. And it
Right.
ruins the business.
So it's like, it's one of those things, like, you really have to, it's hard to make those determinations. Like, I think it's one of those things that, depending on the business that's in there, like, I think we cannot look at like Tesla and Elon Musk as the best aspect of a good business person. He has tons of money. He's very successful in doing certain things, but he's not the greatest businessman in the world. And he's also not trying to sell to a masses. He's selling to a very select subset of people. And if he does really well at that, that's great. But when you look at a company like Ford or Toyota or Hyundai and Kia and stuff like that, they're trying to sell to the masses. They need that 1 million, 2 million, 3 million, 5 million car inventory sales to actually be able to make money. So it's like they need to be able to hit all those different demographic aspects of it. So you can start to see how that's important, to be able to figure those things out. All right, because we're going to keep talking about this forever, let's move on. All right, so a couple quick definitions before we move on. So the first thing is called the sampling distribution of a statistic. So we can look at, so what are the main statistics that we have? Like mean, standard deviation, proportion, those type of things. So we can look at the single sample and get the mean, the standard deviation, and stuff like that. But we also want to be able to do that for multiple samples. So if we're looking at the mean of 100 different samples or all possible samples, that would then give me the mean of the population. So we can look at finding mean for a population in different ways. So if we're looking at a bunch of means, that gives me a better estimation of what the population is. That's what the sampling distribution of a statistic is. A point estimator is that single value calculation. So we're trying to determine, when we get that number, this is what I really think the population is going to be. That's what a point estimator is. The names aren't really as important as the concept is. All right.
I have a question.
Yeah.
So would a point estimator, could it be described as like when they call states before they have the actual number? Would that be considered something?
Yes. Yeah. Because that's what based on all the data, that's what they believe the population is going to have. Yes. So that would be a great representation of a point estimate. The estimator can be considered unbiased if it doesn't get skewed. So like when you're looking at those information, it's not going to have any skewed information. So or outliers and those type of things can affect it. So we typically look at mean as a biased parameter because outliers can skew it, correct? However, when we're looking at in terms of multiple samples, the mean actually becomes unbiased because all the different samples actually eliminates those outlier information. So it is considered unbiased if you can use that as an estimator for the population. So like if we look here, if you look at this target, you wouldn't think that was a good sampling, but it's pretty grouped. It's like it's pretty standardized all around. Same thing with this one. Or if you look at these, it's skewed one way or the other. So these would be biased results, and these would be unbiased results. No, the top is unbiased. The bottom is biased. Remember, you want to be able to get as close to the center as possible. So if we're looking at this one here, that's right in the center, right? But if you look at this one, they all kind of rotate evenly around that center. Where in the two biased ones, they're skewed off the center. Okay? They're not all around it. They're in that one corner. So in terms of shooting, these three targets would be great because they're grouped very well. This one would be bad, but that's not what we're looking at. And so these would be biased. You'd need to fix your sights. These actually would be good. Your sights are correct. You're just not a very good shot. So unbiased estimators, your sample mean is an unbiased estimator of mean. So if we look at our sample means, we can use that to determine the mean of the population. If we look at our sample proportions, we can use that to determine the proportion of the population. And sample variance or sample standard deviation, we can use that to determine the variance or standard deviation of the population. So these are unbiased estimators. And those are the ones we're going to look at. Okay, everybody go with that? You don't need to write down all the words on there. Just those are the three things that we can look at to estimate the populations. All right, how we're going to actually do all this math that we were just talking about. Okay. Remember what I kept saying As long as we have more than 30, we're good. As long as there's more than 30 of the numbers, we can probably pretty much predict that it's going to be a normal distribution. This is why. So if it's a sufficiently large random sample, i.e. the number is greater than 30, which most of us in here probably would not think of as a large sample, but as long as it's over 30, we can consider it a random sample or a large sample, as long as it's random. So significantly large random sample. 30 is great for the sample size, but it has to be random. It is drawn from a population with a mean and a standard deviation. The distribution of the sample mean will have the following characteristics. It'll be approximately normal, which is what we were just saying. The mean of the sample would equal the mean of the population. And the standard deviation of the sample equals the standard deviation of the population, divided by the square root of however many we're looking at. So my standard deviation for the sample is going to be the standard deviation divided by the square root of the number of people. So out of all the formulas you need to remember or need to use, that's the one that you're going to need to use and write down. That's the one we're going to be using. What happens as the number on the bottom gets bigger? To a fraction. Yeah.
Smaller.
So the fraction gets smaller, right? As the number on the bottom of a fraction gets bigger, the fraction gets smaller, correct? Remember that from elementary school and middle school and stuff? Okay. So as that number right there gets bigger, the bottom gets bigger, right? And that means my standard deviation gets smaller. Standard deviation, the smaller it gets, what happens to the graph? Standard deviation tells you how much it's what? Yeah, it's spread, right? It tells you spread, correct? So the smaller the standard deviation, the more compressed it's going to be. So as that number gets bigger, we have a tighter and tighter graph. Okay. So remember, we're doing samples. So unlike before, when we were looking at chapter 6 through 8, we were looking at a single number. Okay. We're looking at one. So the n would have been 1 in all that respect. Okay, because every single individual piece was one number. Now we're looking at samples. So in this case, if my sample size was 25, I have the spread line. And that means I've done a whole bunch of samples that were 25. And I want to use that to determine what the main population is going to be. Well, since 25 is not that big of a number, it's kind of spread out. So that means I could be over here, I could be over here, I don't really know. As I use bigger and bigger samples, so if I get up to the 200, I have a pretty good shot that it's going to be somewhere in between here. Like I know I'm getting closer and closer to what I believe my mean would really be. Okay, does that make sense? Or no? Yes or no?
Yeah.
Okay.
So are you saying that like less deviation in the data makes really much better?
Yeah. So remember, you're looking at, so in this case, we're not looking at individual things. So like when it says n is 200, that means, let's say every single one of you in here went out and asked 200 people their information. Okay. I now have 20 samples of 200. Okay. So really we asked 4,000 people. So my number is really high. I have 20 samples of 200. That's going to give me a good collapse. It's like, okay, I'm probably going to be somewhere in here for the actual population because we just asked so many more people than we would have if we were looking at, say, 50 people. Does that make sense? That's why the higher that number, the skinnier that graph is going to be. So if I looked at all of your means, they're probably going to be relatively close together in that respect. All right, I think, yes, let's actually do a problem. All right, let's do a couple problems. So in this case, my population has a mean of 30. So my population is a mean of 30 and a variance of 25. So what's my standard deviation?
Is the variance the S or the cursive O for standard?
Both. It depends on what you're looking at. If it's a population, it's the cursive O. If it's a sample, it's the S. So variance is in both. You can have population variance, you can have standard sample variance. So these are population. So that's why they're that. The only difference between variance and standard deviation is the square root of the variance. So what's the square root of 25? 5. Very good. Did you say it?
Yeah, and I don't want to say it.
Huh?
I didn't want to say it.
Oh, okay. 5. So that's my standard deviation. All right. So if the sample size of 100 is drawn from the population, so that right there is my N. My N is 100. What's the probability that the sample mean will be larger than 31? So I want to know if X is greater than 31. Does this problem look familiar? The only difference between this is the N. All right, this is no different than what we just did in the last class. Okay, the difference is where we're going to use my standard deviation for the problem. I'm now dividing by the square root of 100. So my standard deviation is going to be a lot closer than just using the 5. Okay, because before we were looking at individual pieces. So my standard deviation was 5. Now I'm looking at this a group of samples. So it would be a lot smaller of a range. So think about it this way. If I'm going to look at, so when shipping containers come in and drop stuff off, do they look at every single shipping container that comes in? No. They're going to grab they're going to grab a couple of them, and they're going to look at everything in it. Okay? That's that sample. So same thing with like cereals and stuff like that. They're not going to look at individual cereal boxes. They might look at a case and say, okay, we're going to weigh this case. Then it means the average of this case is this, or the mean of the case is this. Not necessarily individual boxes, but the mean is that. That's a sample. That's what we're looking at here. All right, so we found our standard deviation. We have our mean. We have our number. Let's find the sample standard deviation, or not sample, the standard deviation of my sample mean. So we're going to take my, and it's the standard deviation divided by the square root of n. So in this case, it's 5 divided by the square root of 100. So what is 5 divided by the square root of 100? Right. Or 0.5. For these, decimals are fine. All right, we good to there? We good so far? Good. I want to know the probability, which means I need to find my what? I need to find my percent. How do I find my percent? I gotta get my z-score. We're going right back to z-scores. Gonna do the exact same thing we were doing before. So you still need that table. So how do I find my z-score? It was x minus the mean divided by the standard deviation, which in this case is that 0.5. So in this case, it is 31 minus 30 over 0.5. Which is what? 2.
You're looking for if it's greater than. Would there be one of those factors?
Nope. I know what you're thinking. Nope. These are continuous. All these are. So we don't have to do the correction. Your mean will always be continuous because you can always have every possible number between them. So if you're doing sample, you don't have to worry about that, the correlation, the correction value. All right, so my z is 2. So we're looking for greater than that, right? So we're looking for that section over there, correct? All right, so if z is 2, what's my z-score for that? 0.9773. Is it? Oh, you have 2? Okay. I got a different table up here and I didn't grab the other ones. I grabbed the one that was sitting over here. And apparently it rounds differently. That's fine. So 0.9772. Is that the answer? Why? Yes. So we got to do 1 minus that. So 0.228. Oh, no, sorry, 0.000228. So that is my answer. Okay. So the chances of a sample mean being greater than 31 is 0.0228% or probability, not percent. Okay. What's 1 divided by 5? Yeah. Almost.
Oh, 1 divided by 5. Oh.
It's
sorry,
0.2.
Yeah.
What was 0.2 on your Z table? Is 0.5793? Okay. That's a way different percent, right? Way different probability. Because we're looking at a sample, we're looking at a group of values. My standard deviation is smaller, which gives me that saying the odds are that's not going to happen very much. Okay. So if I was looking at this was a box of a bunch of different things and it was a weight, I would expect the weight of that box to be 30. The chances of it being greater than 31 is only 2%. So if it was greater than 31, I might want to take a chance and look at that because it might be out of the values that I want to look at. Because there's only a 2% chance that it's going to be out there. So that could be a problem. Okay. Since we're not looking at individual pieces, that matters. All right. Let's find another one.
Some in boxes, not big enough, so they're very.
I can't tell you that much. I really can't, unfortunately.
You can learn something from those observed variations.
Now
I do.
How much you hate hawks. All right. So a company fills bags with fertilizer for retail sale. The weight of the bags of fertilizer is a normal distribution with a mean weight of 15 pounds and a standard deviation of 1.7. What is the probability that a randomly selected bag of fertilizer will weigh between 14 and 16 pounds? How many bags are we looking at in this situation? We're looking for a randomly selected bag. One bag. This is exactly what you did in chapter 8. Find me the probability between 14 and 16. You're thinking too hard. Find me the z-score for 14. Find me the z-score for 16. Find the probabilities and subtract them. I can tell this one. I'm like, you're thinking way too hard about this. Is the yeah, between 14 and 16. Similar, except you're looking inside instead of outside. And it's opposite. So the problem gave you the 5 and the percentage, and you had to find the 14 and 16. In this case, you got the 14 and 16, you want to figure out what the percentage of between them. So my z's were negative 0.59 and positive 0.59. Remember, z's are always rounded to 2 decimal places because that's all you have on your sheet. So 0.2776. And 0.72240, or so, sorry. And now we're going to subtract those two because we're looking between them. So if I'm just going to grab a bag of fertilizer off the line or off my shelf and weigh it, the chances of it weighing between 14 and 16 pounds is 0.4448 or 44.48%. Okay. Does that make sense? All right. Question B, if we're looking at 35 bags. So basically we're going to take a pallet. Okay. And we're going to weigh the pallet. Does that give me the weight of every single bag on the pallet? Individually? No. It's going to give me, I can find the weight of the entire pallet, right? So if I find the entire weight of the pallet, I can divide by 35 and I can get the mean or the average weight of all the bags, right? Because some might be heavier, some might be lighter, but that's the average weight of all the bags, correct? Does that make sense? That's what we're doing here. Now I've got I'm taking 35 bags. What's the probability that the average weight of 35 bags will be between 14 and 16 pounds? So if we look at the same problem, we're going to do the exact same thing, except for one difference. What's the one thing that changes? The number of bags is now 35, so N is 35, but what does that change in terms of what I did up in A? The mean doesn't change. Yeah, the standard deviation changes. So my standard deviation is now 1.7 divided by the square root of 35. That changes. The mean doesn't change. The x's are going to stay as 14 and 16 for this problem, but the standard deviation changes. So now my standard deviation is 0.29 instead of 1.7. So what should that do to that number? Is it going to increase it or decrease it? Yeah. Okay. Let's see. Find my X and Y's. Same thing we did before. That's okay. So you're going to do the exact same thing here. The only difference is 1.7 becomes 0.29. That's the only thing that changes. Your table goes up to 3.49, right?
Yeah.
Okay. So if a 1 pound variation in my bags are okay, and I weigh one bag, I don't really get a good idea if it's good or if the whole setup is good or not. But if I weigh a pallet of 35 bags and I got a average weight of 13 pounds, that's a problem. Because pretty much all of them should be between 14 and 16 pounds. So if you get something outside of 14 to 16 pounds, there's an issue. And it's a lot easier to weigh a pallet of 35 bags than it is to weigh one bag. It's a lot easier to weigh the weight of a truck that's already loaded with a bunch of stuff than it is to weigh one. And you have a really good idea of what's going on in that case. Does that make sense? So if we're having a shipping container full of grain, I can weigh the entire shipping container and figure out that weight and not have to worry about necessarily weighing every single thing inside of it to determine if I'm good or not. Because that's going to give me a lot bigger sample size. All right. We're good for today. Edward, you're saying to do your test, right?
Yeah.
Okay. See you guys on Wednesday. If we must, right?